So today we're going to be starting a new type of word problems, which are called related rates problems. Here's the idea behind a related rates problem. In the real world, the rate at which one variable changes can directly affect the rate at which something else changes. For example, if the radius of the pumpkin gets bigger, then automatically the volume of the pumpkin will also get larger. So, if you start off with a pumpkin with a small radius, as soon as that radius gets bigger, the volume of the pumpkin will also get bigger. So as the radius gets bigger, the volume also increases. If a ladder is sliding down a wall, so we've got a wall, we've got a ladder leaning against a wall. If the ladder slides down the wall, then the base of the ladder, this point, is going to slide away from the wall. And therefore, the height that the ladder reaches will decrease. So three things will be changing. The top of the ladder will be sliding down. The base is going to get further away, and the height that the ladder reaches will be less. These are all connected. As one piece of this puzzle changes, it affects the rate at which other pieces of the puzzle change. Now this means we're going to have equations with multiple variables in them. Unlike optimization problems where we usually used substitution to get rid of a variable, in related rates problems, we will often have more than one variable. And as a result, we need to review how to take derivatives of equations that have multiple variables that are all changing. So let's start with this. Let's assume that the radius of a sphere is a differentiable function of t. What that means is that the radius is changing over time. So it's kind of like this pumpkin. It's growing, so the radius is getting bigger. And V is going to stand for the volume of the sphere. Now let's pause there for a second. If the radius is getting bigger or smaller, then it makes sense that the volume would also be changing. So both of these variables in this problem are going to be changing, and they're probably going to be changing at different rates. Just because the radius increases by 1 inch does not mean that the volume increases by 1 inch. They affect each other, but they're not the same rates all the time. Find an equation that relates dv dt and dr dt. In other words, the rate at which the volume is changing should be related to the rates at which the radius is changing. Let's just start with the volume of a sphere formula. So the volume of a sphere would be 4/3 pi r cubed. And this is a formula that we expect you to know. Because the volume is changing and the radius is also changing, but these are both changing with respect to time. So over a year, the radius gets bigger and the volume gets bigger. Then we can take the derivative with respect to time. So we're going to take the derivative of this formula with respect to time. Now in the past, when we've taken derivative of a formula like this, we've written dv dr. dv dr means that the volume is changing with relationship to the radius, but this time it's not. This time the volume is changing with respect to time. So we would write dv dt, the volume is changing over time, and then when we take the derivative, we would drop the 3, so we would get 4 pi r squared times dr dt. Just like when we would take the derivative and we used implicit differentiation, which meant that we had to put a dy dx every time we took the derivative of y. Because r is changing over time independently from the volume, we have to put a dr dt every time we take the derivative of r. So dv dt, changing with respect to time, would be equal to 4 pi r squared dr dt with respect to time. This would be our formula. And it is a relationship between this rate and this rate. So it satisfies the question we were being asked to figure out. This idea that we are taking the derivative with respect to time is what makes this a related rates question. And what that means is every derivative we write in the question will be over dt because everything will be changing with respect to time. All right, let's try this again. So assume that the radius and the height of a cone are differentiable functions of t, and v is the volume of the cone. When it says that the radius and the height are differentiable functions of t, that means the radius and the height of the cone are changing over time. Now obviously if you make the radius of a cone bigger, it's going to affect the volume. If you make the height of a cone taller, it's going to affect the volume. So V, which stands for the volume, is going to be affected by the fact that the radius and the height are changing. Now the radius and the height do not have to be changing at the same rate. So maybe the radius is growing at 2 inches per year, but the height is growing at 1 inch per year. Because they don't have to be the same rates, we have to examine their rates separately in the derivative. Let's start with the volume formula for a cone. The volume of a cone will be 1/3 pi r squared h. And again, this is something we expect you to know how to do. So we expect you to know that formula. Now we want to find a relationship between the volumes change over time, the radiuses change over time, and the heights change over time. So we are going to take the derivative of this formula with respect to time. Which means we get, if we take the derivative of volume, we just get dv dt. Now the 1/3 pi is really just a coefficient. This is basically just a number times the variables. So I'm going to put the 1/3 pi here, and I'm going to work on taking the rest of the derivative after that. Because the r and the h are two separate variables that are changing independently, we're going to have to take a product rule derivative here. So we would copy the r squared, and then we would write dh dt, because even though the derivative of h would be 1, we have to multiply by the derivative of h over time. So it's kind of like when we put a dy dx instead of 1 when we took the derivative of y. Plus, we would copy the second function and then take the derivative of the first function, which would be 2r, and then dr dt, because the radius is also changing with respect to time. So every single time we take a derivative of a variable here, we divide by dt. We have to do that. All right, so if we simplify this just a little bit to make it look nicer, we would have dv dt equals 1/3 pi times r squared dh dt plus 2hr dr dt. Now you'll notice that in this formula, we have a dv dt, we have a dr dt, and we have a dh dt. So this satisfies our question, which is, can you find a relationship between those things? Just like when we were taking the derivative of a y, we had to write dy dx. In these types of problems where every variable is changing over time, every time we take a derivative, we have to write that d variable divided by dt. All right, so what kinds of problems will we actually be doing here? Before we fill in some common formulas and some steps, let's just sort of talk through this. It's going to start the same way. I would draw a clear and labeled picture. Do not put any numbers in the picture unless they are going to be constants in the problem. Remember, in these problems, almost everything is changing over a certain time period, so there will be a lot of variables and not a lot of numbers in the picture. Then, next to the picture, we're going to list the variables and their derivatives. We're basically just going to say, hey, if we have all these variables, let's write them all down and let's fill in what we know so far. Next, you're going to write an equation that relates the variables. Think about common formulas that you know. Finally, you'll take the derivative of that equation and then solve. Make sure your answer has units. This is where we fill in the numbers. We never fill in numbers unless they are not changing, unless they're constants until the very end of the problem. So what are some common formulas that come up? Well, as we work, why don't we fill in what formulas we use? Today, we're going to start with formulas that involve Pythagorean theorem. So let me show you a few examples. An airplane is flying towards a radar station at a constant height of 6 kilometers above the ground. If the distance s between the airplane and the radar station is decreasing at a rate of 400 kilometers per hour when s is 10, what is the horizontal speed of the plane? So, draw a picture. An airplane is flying towards a radar station. Usually, radar stations are on the ground. And if an airplane is flying, hopefully it's in the air. Now it says, and this airplane, by the way, is flying this way. It's flying towards the radar station, which is on the ground over here. It says in the problem that we are flying at a constant height of 6 kilometers. What that means is that this height is 6 kilometers all the time. The reason I'm putting a number there is because it is constant. It is never going to change. If the distance s between the airplane and the radar station, so let's talk about that. Here's the airplane, here's the radar station. S must be this distance, is decreasing at a rate of 400 kilometers per hour when s is 10. A lot of students are tempted to label this 10. The reason we would not label that this is 10 is because it's changing. We're getting closer, so this distance is shrinking. What is the horizontal speed of the plane? Horizontal speed would be this rate, horizontal. Because I can see that there's a triangle kind of coming into fruition here, it's kind of building here, I'm going to put an X here as well. One thing I noticed right away in this problem is that this is a right triangle. So I know that the formula I'm going to be dealing with is Pythagorean theorem. And based on the picture, I can see that there are two relevant variables. There's the s and there's the x. Because both s and x are changing, the distance here is getting smaller because this is getting smaller. I would write ds dt and dx dt. This is the whole listing your variables and listing what you know. We've got s and x, we've got the rate of s, we've got the rate of x. Now let's fill in what we know. We know that the distance between the airplane and the radar station is decreasing at a rate of 400 kilometers per hour. So this distance s is decreasing, which means negative, 400 kilometers per hour. That's the rate at which that distance is changing. When s is 10, so right now, at this moment, s is 10. What is the horizontal speed of the plane? Meaning we want to know how fast this part is changing, because that would be the speed that the plane is moving, because the plane is flying sideways. All right, now, A formula that would relate the s and the x and the 6 would be s squared equals x squared plus 6 squared, which would be s squared equals x squared plus 36. Now I also know that if right now s is 10 and this is 6, I can calculate x. So 10 squared is 100, minus 36 is 64, and when I square root that, I get 8. I don't know whether I'm going to need to know the number 8 in this problem, but if it's something that I can calculate, it's probably not a bad idea to do that. Once you have a formula set up, your second step would be to take the derivative. So the derivative of s would be 2s and then ds dt because it's changing over time. The derivative of x would be 2x and then dx dt because it's changing over time. And the derivative of 36 would just be 0. Now, based on this information, I can fill in those numbers. So 2 times 10 times negative 400 equals 2 times 8 dx dt, which means I get negative 8,000 equals 16 dx dt. So if I divide, I get that dx dt would be negative 500, because 16 goes into 85 times. Now the question here is, what is my units for this problem? The units would be kilometers per hour because it's how fast the plane is moving. So if we think about one common formula that's going to come up in these problems, it's going to be the Pythagorean theorem. Let's do another problem that requires us to use the Pythagorean theorem. So a 6-meter ladder is against a wall. If the bottom is pulled away from the wall at a rate of 1/2 meters per second, how fast is the top of the ladder sliding when it reaches 3 meters up the wall? Let's start by drawing a picture. We have a ladder leaning against a wall, which means the ladder is here. It is a 6-meter ladder. Now, 6-meter ladder isn't going to change. Even if the ladder slides, the actual length of the ladder itself is never going to change in size. So I can label that because it's a constant value. It's never changing. Now, the bottom is being pulled away, so it would be a good idea to label the bottom with x. The reason I'm using a variable here is because that distance is changing as I slide the ladder away. And the top is sliding down. So I'm going to label this y because, again, if the top is sliding down, then it's changing. Based on this picture, I think a good formula would probably be the Pythagorean theorem. So I'm going to start by listing my variables. Let's fill in what we know. The bottom is being pulled away from the wall at 1/2 meters per second. That means that x is getting bigger because the bottom is sliding away from the wall. So I would write 1/2 meters per second, and I'm leaving it as a positive number this time because this is getting bigger. If it was being pushed back towards the wall, I would make it a negative number because x would be getting smaller. How fast is the top of the ladder sliding when it reaches 3 meters up the wall? So right now, this height is 3 meters. Now I know that a variable that relates these variables is x squared plus y squared equals 6 squared, which is Pythagorean theorem. So an equation that relates these variables. If I take the derivative, or actually, you know what, let's use this equation and let's simplify it a little bit. X squared plus y squared equals 36. And let's go ahead and use the number 3 and see if we can calculate the x value. So if I plug the number 3 in here, I get 9. 36 minus 9 would be 27. and the square root of 27 would be my x value. Now I'm going to take the derivative. So 2x dx dt, because it's changing, plus 2y dy dt, because it's changing, equals 0. The x and the y are both changing here as the ladder slides. So I would have 2 times the square root of 27 times 1/2, and I'm filling these numbers in by looking up here, plus 2 times y is 3, dy dt equals 0. Now the 2 and the 1/2 here are going to cancel. So as part of the process of solving, I'm going to subtract the square root of 27. So 6 dy dt equals the negative square root of 27, which means dy dt equals negative, let's see, 27 would be 9 times 3, so 3 root 3 over 6, which would be negative root 3 over 2. Now, does it make sense that this number is negative? Well, it's sliding away from the wall, so the top is going to slide down. So yeah, it makes sense that it's negative. And my units here would be meters per second, because it's a distance, so it's going to change in the amount of meters over time. All right, last example of these notes. A boat is attached to a dock by a rope that is being pulled in towards the dock at a rate of 2 feet per second. Let's draw a little picture. So here's our dock. Here's the water. A boat is being pulled in towards the dock by a rope that is attached to the boat at a rate of 2 feet per second. If the rope is anchored to the dock at a height of 20 feet above the boat, so this is 20 feet above the boat, how fast is the boat moving when the rope is 45 feet long? Now, how high this isn't going to change because it's anchored there, which is why I labeled it with a number. But I'm going to use variables, so I'm going to talk about this is the rope and this is the x because it's going left and right. I usually use x's for that. And those are both changing as I reel in the boat. So I need to list my variables: rx, dr dt, dx dt. Let's fill in what we know. We know that the rope is being pulled in towards the dock at a rate of 2 feet per second. So the rate of change of the rope will be negative 2 feet per second. Now, why does it make sense that this is negative? Because the rope is going to get shorter as I pull it closer. The rope is anchored 20 feet above the boat. How fast is the boat moving when the rope is 45 feet long? Again, I think a good equation here that relates these variables would be Pythagorean theorem. So x squared plus 20 squared equals r squared, which means x squared plus 400 equals r squared. I think you could probably figure out the x by just using this equation right here. I don't happen to know what 45 squared is off the top of my head, so I'm going to go ahead and type that in. So 45 squared minus 400, and I believe the square root of 1625 is 40.3 something. Square root of 1625. All right, so once I know all of the numbers except for dx dt, which is how fast is the boat moving, so that's going to kind of make sense. The boat's going to float this way. Now I'm going to take the derivative. So 2x dx dt equals 2r dr dt, and I'm making sure I put the dx dt and the dr dt because those are changing with respect to time. Now I'm going to have 2 times the square root of 1625 dx dt equals 2 times 45 dr dt. So if I simplify this, the 2's cancel. Ooh, I forgot to fill in the negative 2 here. Just kidding. So I get the square root of 1625 dx dt equals negative 90, which means if I divide, I get, let's see if we can do this on our calculator here. Negative 2.233. And this would be measured in feet per second because it's how fast the boat is moving. Okay, so the only real big change here is that we're going to have to be putting dr dt's, dx dt's derivatives with respect to time when we're taking these derivatives. Other than that, the process is basically draw a picture, list the variables, list the derivatives, write the equation, take the derivative of the equation, simplify and get your answer. Okay, we're going to do some more of these in practice tomorrow, and I'll see you then.